Hi again, guys. In the last video, we saw that if we incrementally added up the area, let's see if I can kind of get you an idea of incremental. If we incrementally added up the area, just kept adding up the area underneath this curve and plotted that value as we went along incrementally adding up, we would actually come up with this curve, which, again, the black curve represented actually a piecewise function, but it represented acceleration of a patrolman. And we found out that by incrementally adding the area and counting the area below the x-axis as negative, we could come up with this velocity of the patrolman. So adding area got us from the area under the acceleration curve got us to the velocity curve. Well, let's go take a look now at the patrolman's velocity curve we've just seen. Well, his velocity is in, let's see, of course, miles per hour. And so we have the nice graph miles per hour to hours. Well, again, we think about adding up the area incrementally. So in this case, maybe we could just keep moving our line over, getting these little triangles. Of course, we could try to think of adding this triangle up, and we would have the we'd have the area under the curve under that whole triangle. But we could do it incrementally. And so let's see. It looks like the base of this triangle is 1, the height is 60, and 1/2 base times height. So the area under here should be, for example, 30. Okay. Well, what is that area telling us? The area between the velocity curve and the x-axis, we could do it incrementally. What might it tell us? Well, just using our last intuition, got miles per hour times hours, going back the other way, this just could give us his distance in miles from his starting point. We thought of him starting at point 0. So adding up all the net area under the curve as we go, okay, we could go calculate that, but adding up all that area eventually would give us, let's see, so we can see it when x is 1, our net area would be 30. When x is 3, we were at 30 already at 1. When x is 3, we've got a base of 2 and a height of 60, so it's another 120, so we would be at 150 there. At 3.5, we've got another positive area because we're above the x-axis. And again, let's see, this is going to be, the base is 1/2, the height is 60, so that is going to be, and we got to do 1/2 times that, so that's going to be 15 we're adding there, and we're not adding any more, no area between there. Here it's negative, so we're going back the other way. And if we were to plot what we get as we add up all those areas, we would get this red function, which is the position function. So again, this is the big idea. We have gone from velocity to, I'm sorry, we started with acceleration, the acceleration curve. We've gone from acceleration to velocity, and from velocity now to position by doing what? By adding area under the curve. Here I'll just say add net area. And we go from acceleration to velocity by adding the net area. We went from velocity to position by adding net area. Okay, so wow, I mean, that seemed like that's really cool. And we take into account, let's remember one other little thing. Before, we would start with position. I think we used to call it S of t, is the position function. And then we found that velocity, v of t, was s prime of t. So we go from position to velocity by taking the derivative. So this was just taking the derivative. And then v prime of t, which of course is s double prime of t, gives us, we found out, acceleration. Okay, so we went from position to velocity to acceleration, and each time we just took the derivative. So it sure looks like we're just going two different directions. In one, we're going back this way by adding the area under the curve. And then we can come back and go like position, velocity, acceleration by taking the derivative. So that's the big idea for the lesson thus far. I'm going to do a lot more with this, but this was just a short introduction. Talk with you soon.